So in the last 4 videos, what we did is we talked a little bit about the motivation for Gauss's law, the idea of electric flux, and how the total enclosed charge comes into this problem. In this video, what we're going to do is go through a specific example and sort of put everything all together to talk about what Gauss's law buys you. So the first thing we're going to start with is this idea of the total electric flux, which is the integral over an enclosed surface of the electric field. And we found that that was equal to the total enclosed charge divided by epsilon 0. So we're going to do that with an example. What we're going to do is we're going to take a long rod of length L, and we're going to encapsulate that rod with a cylinder. So it's an imaginary cylinder that has a height d and a radius of r. Now this is what we would call a Gaussian surface. So it is an imaginary surface over which we are going to calculate the electric flux. Now the thing to pay attention to here is we have made this Gaussian surface very small compared to the length of the rod. That is that the rod itself is much longer than the length of the Gaussian surface. The reason for doing that is because the electric field in that case is going to be oriented perpendicular to the Gaussian surface everywhere, and it's going to be the same magnitude everywhere. And that's important when working with Gauss's laws, we'll see in a moment. Now this rod has a total charge of Q, but it's distributed along its entire length. So it has a charge density, which is a charge per unit length of Q over L. So the first thing we're going to do is we're going to deal with the far right-hand side of this idea of Gauss's law, which is that what is the total enclosed charge in this Gaussian surface? So that total enclosed charge is whatever amount of charge sits inside of that cylinder. So the total enclosed charge is going to be equal to the charge per unit length times the length of that cylinder, which simplifies into quantities that we have, Q over L times D. So it's a very small amount of charge given this relationship. Now, what we have to do is then deal with the left-hand side. There were 2 things that we learned about from the previous video. One is that we want the electric field and the area vectors to be oriented in the same direction if we can. And we would really like that electric field to be constant in magnitude over the surface, right? Those are the 2 things that we really want. So by making this Gaussian surface very short compared to the length of the rod, we ensure both of those things. Namely, that the electric field points perpendicular to the surface everywhere, and that it is the same magnitude no matter how we rotate it. Now another way to think about that is to take the rod itself, and you're looking at it this way, rotate it 90 degrees. Nothing changes. Rotate it another 90 degrees, nothing changes. You can rotate it by any angle and nothing should actually change. So that means that the electric field magnitude should actually be the same everywhere on that surface. So with both of those things satisfied, we can start to calculate that total electric flux. Now the thing I want to point out to you is that that flux is due to the side, right? This sort of piece that goes all the way around. But it's also due to the top and bottom of our cylinder. It's a total flux, so it's encapsulating the entire rod. So in this case, it's the flux due to the bottom, plus the flux due to the top, plus the flux due to the sides. Now the thing about the top and bottom is that the electric field actually sort of skirts along and it is perpendicular to the area vectors in both cases. That is, it sort of is parallel to the surface or perpendicular to dA. So in that case, there's no flux through the top and bottom, which is what we talked about in one of the previous videos. So we don't expect any flux contribution from the top and bottom, and everything comes from the sides. So this makes our problem even simpler. That is that the total flux is equal to the flux due to the sides, which is equal to this integral that we're going to have to deal with, E dot dA, and that is equal to the total enclosed charge over epsilon 0, which is going to be equal to Q d over epsilon 0 L, based on the stuff that we actually have calculated already. So the first thing we have to do is deal with the electric field and its orientation with respect to dA. As we said, because of the way we constructed the problem, that dA vector is parallel to the electric field, which means while we don't know what the electric field actually is, we do know that the integral of E dot dA is actually simplified into an integral of the magnitude of E times dA because they are oriented in the same direction everywhere on the surface. The other thing that we've done by making the Gaussian cylinder small compared to the rod is to ensure that the electric field is the same magnitude everywhere on that surface, which is critical because we want to take the electric field quantity out of the integral altogether. So we can do that because of the way that we've constructed the problem. And so what we're left with is calculating the total area of just the sides of the cylinder, right? The total area of the sides of the cylinder is just the circumference of the cylinder times the height of the cylinder. So it's going to be 2 pi capital R times d. So this is a canonical Gauss's law problem. We are able to argue that the electric field and the area vectors are oriented in such a way that we can get rid of the dot product. And we're able to argue that the electric field is constant over the surface, and so we can pull it out of the integral, and we're left with just the electric field times the surface area that we cared about. Now, the last thing to do is to relate these two things and to see what Gauss's law gives us, which is essentially the magnitude of this electric field associated with a charged rod. So if we relate these two things, the total flux is given by the electric field times the surface area of the sides, but it's also equal to the charge enclosed divided by epsilon naught, so QD over epsilon L. This gives us that the magnitude of the electric field associated with a rod, in this case, is going to be equal to Q over 2 pi epsilon 0 L R. So that's different from the electric field that you've seen for a point charge, right? It depends on the distance inversely, but not the distance inversely squared. The other thing that I want you to notice is that the d's here canceled out, right? So the size of the Gaussian surface, the height of the Gaussian surface canceled out. That's an important feature, actually, of Gaussian surfaces. The only things that they should depend on, or the only thing that the result should actually depend on, are quantities that are defined in the problem, not the actual Gaussian surface itself. Now, the R actually comes in because we chose a distance from the surface, distance from the rod out in space. But this piece, how high we chose the Gaussian surface, should not come into the problem at all, should not come into the result. That shouldn't show up. So what we end up with is something that is a quantity that depends on some constants, but depends on this sort of 1 over the distance from the center of the rod out, which is different from the point charge. So to summarize, what we've done here is we've used this Gauss's law to figure out the total flux due to this rod. By doing so, we were able to recover an electric field due to the rod that's different from the rod, different from a point charge electric field. It also matches the electric field that we have calculated for rods before when we did it through integration. But it's a much simpler approach in the sense that you didn't have to add up all the chunks. You had to think about the shape of the electric field and how it relates to the Gaussian surface. So this approach of Gauss's law will work for cylindrical situations, it'll work for spherical situations, and it'll work for planar situations. And those are examples that you'll do either on your homework or in classroom activities.